is Charles Santana. He graduated in the University of Federal de Bahia in Salvador, Brazil, and he did a master in University Feira de Santana, also in Bahia. And he was working on the group of Miranda on using complex networks to understand processes related to climate. And he did a master thesis there on that topic. He then crossed the Atlantic and come here, and he did another master in the Menendez Pelayo. And this way was on meteorological downscaling, precipitation forecasting. And now he's enrolled now he's doing a PhD under the supervision of Carlos Duarte, using network theory to understand food webs and ecology and this kind of problems. Today he will talk about topological properties and robustness of polar food webs. And if you go to the CSIC homepage today, there is news about exactly this work. So, Carlos.
Thank you, Emilio, for the invitation and for the word. Thank you, everybody, for being here. As Emilio told, I'm Charles, and I'm a PhD student at IMEDEA. I'm part of a multidisciplinary team composed by a physicist, that is Alex Rosenfeld, that was IFISC postdoc some years ago. He's now at the University of Centro de Buenos Aires in Argentina and the University of Évora in Portugal. Also, the team is composed by Pablo Marquez, that is an ecologist from the Catholic University of Chile and from the Santa Fe Institute, and my advisor, that is Carlos Duarte from IMEDEA here in Mallorca and the University of Western Australia. And our team is part of the International Laboratory of Global Change, that is a laboratory formed by CSIC, led by CSIC, and formed by Catholic University of Chile and Federal University of Rio de Janeiro, Brazil. So, the title of this presentation is Topological Properties of and Robustness of Polar Food Webs, and is part of my PhD thesis. I will present some results about the vulnerability of the polar food web to global change, and how to assess these vulnerabilities using a complex network approach. When we talk about global change, we are talking about change in the environmental system caused by the human action, especially in during the last century. And the main of this global change that especially the general public know is the global warming. Here in this picture, I present you, it's a picture from NASA that shows a comparison between the temperature in the Earth for the year 2012 compared with an average from the year 1979 to 2000. And it is what we call an anomaly of temperature. So the hot colors means that was recorded. It was recorded an increase in temperature in the region that has hot colors, and the cold color that it was recorded a decrease in temperature. And what I would like you to pay attention in this picture is to the polar regions, because if you pay attention, the polar regions, especially the Arctic and the Antarctic Peninsula, has a record an increase in temperature recorded here that is much higher than the average in the Earth. For all the Earth, it was recorded an increase in temperature about 0.5 degrees Celsius, and for the poles, it was recorded about 1.5 degrees Celsius. So, it's the reason, because of this discrepancy between the polar regions and the rest of the world, our research group has a lot of research projects in these two regions.
So excuse my ignorance. What is the typical time scale for climate change?
Some people study maybe 30 years, but here we are talking about 79.
So 30 years is a time scale for climate change?
No, to compare, we used to study to compare the temperatures of some years with a basal period of time. Some people use a base period of time from 1960 until 1980 as our basal period. But for polar regions, we used to study a period starting in 1979 because it was when they started to look at the sea ice.
No, I understand, but my question is the time scale of 30 or 40 years is a time scale associated with climate change?
No, to climate change, no, but when we talk about climate change, we talk about eras or about centuries. Yes, now we are talking about anomalies of temperatures that indicate that
anomalies as compared to?
Comparing 2012 with an average of the 20 years in this case. My objective here is just to show that the change in temperature in this period for the polar regions is much higher than for the rest of the world.
Much higher means a factor 3.
3, for example, 3 times higher. And it's my intention.
Which is the standard deviation of the period?
Here, I don't know. It's a picture from NASA.
I'm talking which is the standard deviation
of the
temperature in the period 1979-2000.
I really don't know.
So you don't know whether this is significant or not?
Yes.
So you don't know if the factor 3 is within the otherwise?
I don't know, but it's
well, that's the first thing you need to know, right? Whether there is a normal or not. But this is not a good thing to do, so that there are lots of. No, I'm talking about. I know there are other data. Okay, I'm talking about this data. This data are showing a mean value compared with another mean value. I want to know the standard deviation. This is basic statistics. Physics, ABC statistics. 101. Compare the average with standard deviation.
yes. Sorry because I don't have this standard deviation.
No, that's okay. She has on the general motivation, of course, but that's
Yes,
different.
and the next slide, I also don't have the standard deviation, but I know the standard deviation here is about 2 millions of square kilometers. Here is a consequence of the warming in the poles is the sea ice melting. And here in this picture we have the sea ice extent of Arctic during an average between the years 1981 until 2010 and 1979 until 2000. Here in the black solid line is 1979 until 2000, and this gray line is from 1981 until 2010. And what I would like to show you here is that for the recent years, especially 2007 and 2012, the sea ice extent has been lower than these average values, and especially for the summer it has been much lower. I don't have the bars here, but I can assure you that the values of the standard deviation, the two times the standard deviation is 2 million square kilometers. So I'm sorry, but I don't have the proper plot to convince you about the importance of this impact. But continuing, I'm talking about polar regions, and the importance of looking to the sea ice melting is that the sea ice is the main habitat of most of the Antarctic and Arctic species. Also the big species and the small species. For example, zooplanktons depend on the ice because they used to live inside the ice, and the big mammals, for example, use the sea ice to hunt. So like polar bear, it needs the sea ice it hunts inside the water, but it brings the prey to the sea ice in order to eat its prey. So sea ice melting is very important to most of the species in the Arctic and Antarctic ecosystem. Also, as we are talking about global change, not only global warming, not only climate change, the overfishing is another impact that has important effects in the ecosystem. and especially in the Arctic, in the Antarctic, there is an overfishing. In the Arctic, especially about an overfishing of predators, of big species like the cod, that in Spain we call bacalao, and in the Antarctic, a big fishery in the krill, that is a small zooplankton, a crustacean, and that is used especially by Japanese and Chinese to produce like an fish oil, but they call a krill oil. So it's another important change that human is improving to the ecosystems, and especially to the Arctic and Antarctic ecosystems, as well as the ozone depletion. We are looking here at the ozone hole that is above the Antarctic continent. Although the gases that produce the ozone hole in the atmosphere has been forbidden in the 70s, but the ozone hole is still there, and it still has impacts in the marine life in the Antarctic continent, especially in the small marine life, the phytoplanktons and the zooplankton, the crustaceans. So I just would like to introduce these impacts, these global change, to convince you that all these impacts have an effect in the polar biota, in the polar life. As I said before, also the small life and the small species and the big species of the polar ecosystems. And here just a distribution of, here it was a meta-analysis work from Carlos and some researchers that identified that most of the reported impacts of global change in the marine species of polar regions, these impacts have been reported for plankton, for bentonic species, that are the species that are in the land, in the deep ocean, but also to marine mammals, seabirds, and fish. And here is the kinds of change in this marine life that was identified. For example, change in the phenology, that is the time of breathing, of reproducing of the species, the growth conditions of the species, abundance, range shifts, etc. So it's just to show you that has been reported a lot of change in species in many different trophic levels in the ecosystem, and a lot of kinds of change of effects. And researchers biologists especially, used to study these impacts in each species at a time. For example, they make in laboratory a study about the conditions of krill under climate change pressures. Or they go to the field in order to look what happens to the penguins and to the polar bears. So they study species individually, independently. But we know that the effects, what happens to a species, also affect its predators or its prey or other species that live together in the same ecosystem. So there is an increasing research field, and you know very well this research field, the complex systems, especially the complex networks approach, that allow us to study the ecological relationships among these species, and to see how the effects of global change in one species can affect all the other species. So we are talking about ecological networks in which each node of the network is a species, and each link between two species is an ecological relationship that can be a mutualist relationship, but can be also a predation. And in my case, I'm talking about predation, so I'm studying what we call food webs that are ecological networks of predation. And we, as I said before, we have the focus in the study of the Arctic and Antarctic ecosystems because they are the most affected by global change right now. And the objective of our work is to understand how would Arctic and Antarctic food webs respond to the effects of global change, considering all the differences and similarities of these ecosystems. The similarities are easy to see. The similarities between Arctic and Antarctic. They are the two regions with more extreme, two of the regions in the world with more extreme ecosystems. So the temperatures are very low. For example, the life is very. We can say that the life is difficult to be there. In Antarctic, there are many regions that it was not recorded any kind of life. But they also are very different. For example, Arctic is an ocean. It's surrounded by a continent that has influence of the ocean, of the Antarctic, of the Pacific Ocean, of the Atlantic Ocean, and it is under constant stress of the water that comes from these oceans. And Antarctic is a continent that is surrounded by an ocean, that is the Southern Ocean, but this Southern Ocean has no interaction with other oceans. His behavior is more constant, and there is no ocean that gives water to the Southern Ocean, for example. So it is under less stress, we can say it, than the Arctic ecosystem. And to study how these food webs will respond to the effects of global change, we propose two complex network approaches. And in order to study this, we are using the two largest food web reported until now, that is for the polar regions. That is an Antarctic food web with about 586 species, with species in the Southern Ocean, and an Arctic food web with 145 species of the Barents Sea, that's the region of the Arctic. These papers are very recent. The Southern Ocean paper is from 2011, the Arctic food web paper is from 2009, and until now we don't have, we didn't found any larger food web than these two examples of food web. So we are using these food webs, and the first study that we did was about the topological properties of these food webs, and especially some properties of the topology of the food webs that I will explain here to you. Here is an example of a food web in which each node is a species, and an arrow that comes in to a species, for example in this case from 1 to 7, it means that 7 eats 1. So some of the index of the properties that we study is the number of prey and number of predators of the food web, in which a species is a prey if it has a degree higher than 0. So if at least one species is eaten a species is a prey if it has a degree out higher than 0. So if at least one species eats this species. In this case, 1 is a prey of 7 because it has a degree out 1. And 7 is a prey of 9 and of 8 because it has a degree out 2. But also 7 is a predator of 1 because it has a degree in higher than 0. So number of predators is given by the degree 0 or the degree in of the node, and number of preys is given by the degree out of the node. And we have also another property that is number of top species. That means the species that has no predators. In this case, 9 and 6 are 2 top species because they have no predators. And also the basal species that are the species that has no prey. In this case, the 1 is the only basal species in this toy food web. Also, another property we study is the connectance. That is the proportion of realized trophic interactions among the total number of potential interactions. So, in this case, they consider as the potential interaction the total number of potential interaction would include the cannibalism, for example. So, in this case, we have 9 species. The total number of potential interaction would be 9 to the square. So it would be 81 potential interactions. if 9 had interaction with each species and with himself. Or if each species has interaction with each other species and with themselves. In this case, we have 10 realized interactions, and the potential total interactions would be 81. So the connectance of this network is 10 divided by 81. Another property that we study is the trophic level. And trophic level is defined as the trophic level of a basal species is 1. So the species that has no prey has trophic level 1 by definition. And the trophic level of each other species is given by the trophic levels, the average among the trophic levels of the prey of the species. So in the case of 7, 1 is a basal species, so it has trophic level 1. 7 has only one prey, that is 1. So the trophic level 7 is 1 plus 1 is 2. And 9, it has two preys, 7 and 8. 8 is at trophic level 1, 2, 3, 8. And 7 is at trophic level 2. So the trophic level of 9 is the average between 3 and 2, that is 2.5. So this measure of trophic levels allow us to have fraction values of trophic levels.
And what is the interpretation of that?
Sorry?
I mean, but does it mean to have a trophic level of 1.3 and another 1.4?
Because no, the importance of these fraction values is because, for example, for the whale, a whale is also a big mammal, a seal, but also it's a zooplankton. So in order to don't choose between the lower and the highest, the higher trophic level, we make an average. It's not my invention, but it's a convention. In order to take an idea about the main possibilities of trophic level of the species.
What does the word trophic mean?
Sorry?
What does the word trophic mean?
The word trophic? It's like the position, because it is a trophic network. The trophic is like when a species feed another species, we call it a trophic relationship. In this case, trophic levels, it means the level in the trophic chain, as we call also trophic chain, or feed chain, food chain, in this case food web. And omnivory level
The trophic level of number 8?
of number 8 is 2, or is 3, because it's the average, but of the 9 is 2.5. And omnivory level, a species is considered omnivory if it feeds species from different trophic levels. So in this case, 9 is on omnivory, but 8 doesn't, because 8 feeds the species from all the preys of 8 are at the trophic level 2, but 9 no. And we calculate the omnivory level with the standard deviation of the trophic levels of the preys. So if the standard deviation is 0, the species is not an omnivory. But if it is higher than 0, it is an omnivory. And to these networks to this food web that I told you before, the first thing we did was to study the trophic levels of each species and to identify the number of preys of each species. And here we tried to represent this difference in the trophic levels and number of preys with these two pictures. Here is the Antarctic food web. Each point of the Antarctic food web is a species, and the size of the species is related with the number of preys of each species. So in this case, the smaller points are the basal species, and the higher points are the bigger points are the predators. And what we can see immediately with these pictures is that the number of basal species of the Antarctic is much higher. The proportion of basal species in the Antarctic food web is much higher than the proportion in the Arctic food web. Also, the trophic levels, we can see here, the green color represents the basal species, the lower trophic levels. So also we can see that the green points are the basal, and most of the Arctic species are at a middle trophic level, about between 2 and 4, but most of Antarctic species are at trophic level, lower trophic levels, especially basal species. And this information, I will come back later. This information is very important to infer about the possibility of a trophic cascade in a food web. Some studies from Bruno and O'Connor says that the increasing predator diversity relative to herbivory diversity should strengthen trophic cascade effect. So that means if a food web has more predators than prey, the probabilities of have a trophic cascade effect is much higher than if it doesn't. And by trophic cascade, I mean that the effect that happens when, for example, the decrease in the abundance of a great predator, for example, the polar bear, affects the abundance of its prey. If I have less predators, so I have less stress, so I can have more abundance of individuals of the prey of this predator. And with more prey of this predator, I will have more stress in the lower trophic levels. So it's the propagation of the perturbations in the food web that comes from the top trophic levels to the bottom trophic levels. So this distribution of basal and top species of predators and prey makes the Arctic food web susceptible to trophic cascade effects. Also, we analyzed other properties, not only the relation between top basal and predator prey, but also the connectance. And for Antarctic, the connectance is lower than the connectance of the Arctic. It's 5 times lower than the value of connectance in the Arctic. So Arctic is more connected. Also, generality and vulnerability are 2 words that means the number of predators and the number of prey. So the higher generality a food web has, that means that the species have more prey to feed. The higher vulnerability, that means that the species have more predators that feeds it in average. And also we look at that the degree distribution of the networks. By degree, we mean the number of connections of a node. So in the case of the food web, is the number of predators and prey of a species. In this case, what we see is that for the Arctic food web, that is the red dots, it was identified exponential decay of the degree distribution. And for the Antarctic food web, we identified an exponential decay followed by a power law cutoff of the degree distribution. What's the importance of these different kinds of degree distribution? Is that food webs that have power law degree distribution are very robust against to random perturbation. That means to the extinction of a species randomly, but they are more vulnerable to the stress of some species, especially of the species that has higher degree. In this case, I will explain here, for example. This degree distribution makes the Antarctic food web more robust against random perturbation, but more sensible to perturbation in the most connected nodes. And in the case of Antarctic, the most connected node is the krill, that is, as I told before, is a small zooplankton. And this zooplankton is under pressure of overfishing, especially of Chilean and Japanese industry of fishery. And it's an important information that it says that the robustness of the Antarctic food web is highly dependent on the krill. is what the degree distribution analysis says to us.
There is one thing that I am a little confused.
Yeah.
In the Antarctic food web,
Yeah.
there is a lot of basic, of lot of trophic of species at the lower trophic level and few at the top.
Yeah.
And you say that is highly vulnerable. I don't understand that. I guess that if you have very few primary producers, the vulnerability should be higher, which is the case of the Arctic food.
Yes,
So in what sense, what does it mean this vulnerability level 2.67 here in front of 1.56 there?
No, it doesn't mean that the Antarctic food web is more vulnerable. It's just a property that says about the average number of predators that a species has.
But if a species does not have a predator, that is not a vulnerability of the species.
No, the name is vulnerability, but it doesn't mean that the food web is vulnerable. It's like the vulnerability of the species.
Yeah, but if I am a primary producer,
Yeah.
and I have two predators,
Yeah.
and one of those predators goes away,
Yeah.
I am not going to be worried about that.
No.
So-
you want it for yourself, your own species.
No, but if you have a food web which has a lot of primary producers, and you say that it's more vulnerable, it's not clear to me why.
No, I understand what you are saying. About this, you are saying it's the effect I told before that is the trophic cascade. I told that the relationship between the number of predators and number of prey of the Arctic food web as it is higher than the Antarctic. So as in Arctic we have more predators than prey, so Arctic is more vulnerable to trophic cascade effect. The name of this property has nothing to do with the vulnerability of the trophic network. It only says that each species in the Antarctic has more or less 2.7, more or less, has in average 2.67. No, sorry, I changed the values. Sorry, yes.
But for our education, who invented this name of vulnerability defined in this way?
No, it is related with the vulnerability of the species, but not the food web itself. I understand. Sorry.
I mean, you're comparing two things that at least they have different sizes.
Yeah.
I mean, of course, if the things are not normal and you have power laws and things like that, there is some bias in the sampling, right?
Yeah.
It is expected to have that. So have you tried to compare these things, just for example, picking 115 nodes randomly from one and see whether the results are different? Because they don't look, well, I don't know.
Yeah, no, we did it, not randomly, but we choose the species at the East Antarctic and at the West Antarctic. Only the species that, because we are talking about the Southern Ocean, it's all Antarctic ecosystem, so it's a higher ecosystem, so it has a high number of species in there. And we choose the species at the East and at the West Antarctic, the records of the East and the record of the West Antarctic, and they had more than it was 240, more than 200 species. It was not 150, for example, but it was a smaller network, and we compared it and we found the same properties. I didn't put it here in the presentation, the talk, but we did this kind of study. But this random choose of the species we didn't, and I think it would be a very good idea. But the referees didn't say anything, so we didn't remember this, but it's a good idea. Maybe we can do it and then see what happened. And so what I would like to tell you here with these first results is that the topology, until now, we didn't do any simulation, we didn't do any extinction, we didn't kill any species to talk about the robustness of the food webs. We only saw the topological properties of the food webs, and we got some information about the possible vulnerabilities of each food web. That Arctic is probably more susceptible to trophic cascade effects, that the Antarctic is more robust against random perturbation but more vulnerable to perturbations in the high degree species, that is the krill. And in the case of connectants and omnivory, Baser and collaborators said that higher values based on experiments and in meta-analysis, they said that higher values of connectants and omnivory makes a network more robust against invasion of species. So in this case, we can say as the proportion of omnivory in the Arctic is about 81%. Omnivorous species in the Arctic are 81% of species. In the Antarctic, 41%. The connectants, although it is a lower value, but it's 5 times higher than connectants. So the connectants of Arctic is 5 times higher than the connectants in the Antarctic. So we can say that the Arctic is more robust against the invasion of species based on these results of Basil and collaborators. So only looking at topological properties, we can say something about the robustness of the ecosystems. But we were also interested in simulate what would happen if one species or anti-species would be extinct. So what we did was what we call secondary extinction simulations. What it means, given a food web, in this case we are choosing randomly one species to be extinct, and if we choose this species, we also extinct the species that depends only on this species. For example, here the species 3 was chosen randomly, and we extinct it, but we have 4, 5, and 6 that depends on 3 to live. 4 depends on 3, and if so, 4 will be extinct. As 4 was extinct, 5 would be extinct too, and also 6. So in the case of the extinction of one single species, we have 3 secondary extinctions in this case. And here, if randomly we choose the species 8, we can extinct 8, but as we don't have any species that depends only on 8 to live, so we don't have any secondary extinctions. So this kind of simulations is in order to study the robustness of the food web, and we did it to different sequence of extinctions. The simpler sequence was the random sequence. Just choose a species and kill it and remove it from the network. And for these random simulations, we perform n squared simulations, in which n is the number of nodes. So in this case, we would perform 81 different simulations to give to each species the possibility to be removed in all possible orders. So one would be the first species to be removed, or the second species, and so on. And once we had this simulation until we had no species in the food web, we would take a look at the number of secondary extinctions depending on the proportion of nodes that was removed. Here we compare this number of secondary extinctions depending on the proportion of primary removed species for Arctic and Antarctic, and we see, for example, each one of these lines is what we call robustness thresholds. That is our Rx. That means it is the point, the proportion of primary extinction in order to have a total extinction of X%. For example, R50 is the proportion of primary extinctions in order to have 50% of the species extincted by primary and secondary extinctions. So it's like this sum, no? And we have R50, R75, and R100 that means the proportion of primary extinctions in order to have 50% of species extincted, 75% of species extincted, and 100% of species. And what we see is that for 50% of species extincted, both Arctic and Antarctic food webs has the same robustness. That means the same proportion of primary extinction in order to have 50% of total extinction. So that means that randomly, at the beginning of the extinctions, we have few secondary extinctions of each food web. This shadow area means the standard deviation of among these n squared simulations we performed. And here's for the R50, but for R75, for example, we see that the Arctic food web needs few primary extinctions in order to have 75% of total species extincted, to be extincted. So it's a way to study the robustness of the food web against two perturbations, in this case, two random perturbations. And here's the total for both. The total, the R100, it was near to the 100% for both food webs.
So this means that both food webs are extremely robust. You can remove half of the species and nothing happens.
Randomly.
Yeah, I mean you remove half of the species and nothing happens, typical.
Yes.
You have to remove at least 75% of the species for something to happen, and then the difference between them is of other whatever.
It was what we thought at the beginning. So it is for random extinctions. Because I will show you later other kind of secondary extinctions that has different behavior. But the final conclusion will be that there are characteristics of each food web that gives to the food web more or less robustness.
The final conclusion is that you can go to Antarctica, drill, and do whatever you want because it's sufficiently robust that
randomly. If you
randomly.
No, yeah, you will mean, because you will see that some species are very important. If you kill randomly, the probability to give a critical perturbation to the food web is very low. But we will see at the next slide.
There should be like something like the strength of the connection between the species should be important, or
no, in this case it's 0-1. It's only if it is connected or not.
Wouldn't that be important? I think about the local kernel model, which is simple.
Yeah, yes, exactly. Yeah, it is actually the third chapter of the thesis. It's not in this talk, but it's important. But another result that we analyze is not only this robustness feature, but also the number of clusters of the resulting food web. And then for the Antarctic food web, it is different from the Arctic food web. The number of clusters resulted from the primary extinctions are much higher for Antarctic, for Antarctic than for Arctic food web. And it is because of the omnivory and of the higher omnivory and higher connectance of Arctic food web. It's like for Antarctic, although we don't have many secondary extinctions, but we separate the food webs. We have different food webs during the primary, due to this primary removal of species. But this is for, as I said before, is for random removal. But we also performed the simulation for the species with more predators. So the sequence of species removed is in the sequence of the species that has more predators are removed first. And here we see it's more fun, for example. For the Antarctic food web, we have a krill that has a lot of, the number of predators of krill is much higher than the number of predators of each other species in the Arctic or in the Antarctic food web. So, when we take the sequence of the most connected species, the species with more predators, if we remove the species with more predators in the Antarctic food web, we have more secondary extinctions than if we remove the species with more predators in the Arctic. But as we are studying only the R50, R75, and R100, we are not studying, for example, the R25. So the robustness of the Antarctic is always higher than the Arctic for the values we are studying. But if we take a look at the beginning of the primary removal, we see that Antarctic is more vulnerable to the removal of the most of the species that have more predators. Also, for the number of clusters resulted by these primary extinctions. And another sequence we performed simulations was the sequence of the next one was the sequence of the species that have more prey were removed first. So in this case, we also have like similar values for Antarctic and Arctic ecosystem. Actually, in the Arctic, the robustness is lower in the beginning of these primary removals because Arctic have more predators than the prey, and also is in the final of in the ending of these primary removals. But the interesting result here is about the number of clusters generated by the removal of Antarctic species. That is much higher than the other examples, the other simulations we performed. So, and as we performed N2² simulations of primary extinctions randomly, and only N simulations of primary extinctions for the sequence of prey and sequence of predators. But for random, we wanted to see what was the impact of each species in the secondary extinctions of the network, of the food web. So what we did was to calculate the average number of secondary extinctions given due to the primary extinction of each species in the food web. I think I cannot zoom it here. No. But what we have is that for Antarctic food web, the Ophasia superba, that is the krill, it has in average 5.07 secondary extinctions due to the primary extinction of the Ophasia superba, and a standard deviation of 3. And the second species with higher number of secondary extinctions due to its primary extinction has only 1.75 secondary extinctions. So the importance of Ophasia superba to the Antarctic food web is much higher than the importance of any species in this food web, and also is much higher than the importance of any species in the Arctic food web. It's like what we are measuring here is that in the Arctic we don't know any species that is very, very important to the stability of the ecosystem, as we know for Antarctic that the Ophasia superba is. And we didn't find any other work that have quantified this importance of the Ophasia superba compared to other species in the Antarctic food web. So, the main conclusions of our work. First of all, we know that Arctic and Antarctic ecosystems rank amongst the most vulnerable ecosystems to the global change, especially global warming.
Can I challenge that sentence?
What?
Can I challenge that sentence?
Yeah.
Can you repeat it? And can you see if this is what you've told us about?
I'm telling that these ecosystems are more vulnerable than the other ecosystem.
Yes, to global warming.
To global change.
To global change. Why? I mean, you've shown us that you have a network which is fixed, and that something different happens in the two types of networks when you randomly or non-randomly remove some nodes.
Yeah.
Now, what's the relation of this node removal to global change?
No, it's not my.
And what is the relation of that to temperature change? And what is the time scale of temperature change and evolution of the trophic network? I didn't see anything of that.
No, in this case.
So you've done a very nice analysis of two trophic networks, but your conclusion?
No, it's not. It's the conclusion of this talk, but not my conclusion. No.
Welcome, Mr. McCoy.
No, the Arctic and Antarctic systems are more vulnerable to the global change. It was what I told at the beginning of the talk as an introduction. They are results of many scientists in many kinds of research fields, but I'm just telling the main conclusions of the talk, not the.
No, what I'm trying to say is just that you're not misunderstanding. I mean, this is very nice analysis of two trophic networks, which is the vulnerability and their resistance and what happens when you remove nodes and whatever. Now you go to the end of your analysis, and then for me, that's my understanding, and I want to know your opinion. You just jump into the vacuum in your conclusions.
No, indeed, it's not my conclusion yet. Because of this analysis, this beautiful plots, the simulations we did, we have conclusions about the vulnerability of the Arctic and Antarctic food webs to global change, if they exist or they don't exist. Because,
but to make this conclusion, you should know something about the time scale of evolution of the networks and the time scale of evolution of the climate change.
No, what I know.
And in which sense climate change is associated with the removal of one or another species. Otherwise, this has nothing to do with climate change.
No, it's global change.
Or global change, whatever. I mean.
No, because climate change is just one part of global change. For example, you cannot say that there is no effect of UV radiation in some species of zooplankton. We cannot say that the overfishing in the Arctic and Antarctic Ocean.
I didn't make any statement that this does not have any effect. I'm just saying that from your scientific analysis, there is no conclusion on the things that you are trying to conclude.
Yeah.
That's my opinion.
Yes.
If I can say something.
Probably comparing.
No. But yes. This is the very same kind of analysis that you do about the structural vulnerability of a network. And it's the same analysis that has been applied for the propagation of epidemics and for many other things. In those cases, you also have time scale, right? So you don't have a flu and then you generate it and then so there is some time scale.
You have an idea of this time scale?
No. What I'm saying is that the first studies that claim to say something about epidemic spreading, they didn't incorporate these time scales. They did that later.
Is that an excuse that others make the same mistake?
No, I'm not saying that this is an excuse, but I'm saying that this could be a first step. And now he has said that he has included Volterra equations to analyze this thing. This is a way to introduce time scales into the system. So I'm just trying to understand, and for me, in a framework that this kind of analysis makes sense, right? So this is a first step in order to understand the structural properties. Of course, evolution and time scales are very important because you have time to adapt and to meet something that you didn't need before, and that's very important, of course. But I put that in that frame, so that's basically paralleling something that has been done in other countries. So it's not an excuse, it's not the full picture, but I understand that as a first step in that.
Preferably if it is understood in that way, but if it is presented as a scientific proof of something, then I have to say I didn't see that conclusion.
But Max, you don't see a problem. I mean, he's speaking about overfishing, and then he wants to see what's the effect of that. I mean, will you ruin the whole biota of the Arctic
No,
by overfishing?
The first transparency had nothing to do with overfishing.
I must have deleted this first transparency. But
Yeah,
it's exactly what Victor told, and it would be the last conclusion that further robustness analysis regarding to the abundance of species are being performed using dynamical predator and migration models for polar food webs. And in these kind of models, we are using time scales. We are using data about the data from the climate models of IPCC, for example, and the effects of these, the results of these models in zooplankton. So there are studies in Norway and other regions that study for each species the effect of the increasing temperature, for each species the effect of the change in radiation, UV radiation. And what we do until now is to study how the topology of food webs can make all these effects, can compound all these effects into a bigger or lower effect in each food web. And in the next work, the work we are performing now, not only in the studying the extinction of species, but also the changing in the abundance or the range shift of species, and this needs the time step. This needs the time analysis.
This is perfectly nice for me, but to establish this link, one has to know something in which way temperature changes affect the removal of given nodes of the trophic network. Otherwise, I mean, this is one thing and this is another thing.
Yes. These are the information about in how, in time, each species of this ecosystem are being affected by climate change or overfishing or any other change. We did not perform this analysis, but we are using analysis other scientists did, and we believe it's a question of.
I like the analysis.
Forget these two first conclusions, please. And no, only the first conclusion, because despite both polar ecosystems are very similar, they present fundamental difference. I have only 1 minute. They have fundamental difference in the food web topology and robustness. And these differences are related to the susceptible of Arctic food web to trophic cascade, because Arctic food web has more predators than prey, and Antarctic food web doesn't. It's related to the vulnerability of the Antarctic food web to one specific species, that is the Antarctic krill, because of the degree distribution of the number of predators and prey of each food web. In the case of Antarctic, it's a power law degree distribution. And here is just to say that we performed some robustness analysis by removing species and looking to the secondary extinctions, due to the primary extinction of some species. And we are saying here that these simulations confirm the importance of Antarctic krill to the Antarctic ecosystem, and also that the high number of clusters for Antarctic food web during the removal, that we find a high number of clusters during the removal of prey in the Antarctic food web, and during the removal of high omnivory and predators in the Arctic food web. So the objective of this work was to compare Arctic and Antarctic food web and to study if those food webs would respond differently to the impacts of global change. And what we found was this, that they would respond differently, and what would be this response. Maybe in 100 years somebody can prove or that we are wrong. But right now, only if we go to the Arctic or the Antarctic, we can kill every species and see what is happening. Maybe we can do. Thank you.
There's been a lot of questions, but still we have time for a couple of more questions. Well, probably it's best on the students first.
This is not an MD seminar.
But if not, I see.
May I comment just one thing? It's the first time I presented this work to not biologists. And I need to say that it's more difficult, but it's more fun also. And I really was needing this feedback, although it's not. I don't agree and they don't agree with me, but I really needed this feedback. So thank you for the comment.
First of all, I appreciate that you're such a good sport in discussing this controversially, but I have even a bit more fundamental criticism than Max. Because it's motivated the work as not a study on web network science. It's motivated by really the vulnerability of Arctic and Antarctic food webs. What attempts are there? This is really for curiosity, because we're doing science here. That this food web modeling has any predictive power? Or could someone just come up with a different model, say I have contradicting results, and
no? For food web models, it's a challenge to have a predictive food web model feasible that considers both biotic and abiotic interactions. So that consider the effects of the warming of or the effect of UV radiation. It's a challenge. It's the most of the work in food web studies use a kind of niche modeling or this kind of robustness study. And the last part of our thesis is exactly a predation migration model that considers the effects of the environmental. We will couple niche models that are just statistical models that relate the presence or the absence of species in a landscape to the environmental conditions of this landscape, and the niche model says to where the species can migrate or not. So we will couple this information to the migration, to the predation model. So we will have different food webs in each landscape depending on the presence or absence of.
Isn't it highly dangerous already at this level to link a study which is on a very basic level to a highly political subject like ecosystems and global change, and give the impression that one would have already input for politicians?
Yeah. Actually, it's the challenge is that it's this. So I don't believe we will have a predictive model, but we will have a beginning of a predictive, maybe a predictive model in the future. We have good results with toy food webs. We have good results with the small real food webs, but until now we don't have good results to big food webs. And I saw some works with small food webs and that were coupled to the global circulation models, and so I guess I think it's the beginning, and I think my PhD student maybe can have good results about prediction of food webs. Okay.
I think so. Your first criticism was that you might come up with 20 different models because of climate change. You will never actually be able to confirm one of them. Because you will have to wait for 50 years.
So you can take Rust's data to try to fit into that? So
yeah, but we have recorded data like this in the past for so many interactions. But what I was just thinking is maybe you can go out of the ecosystem of the Antarctica and you do it with cells or something, to change the framework and to try to do something there and then see if you model this. Maybe it's the wrong angle, but
for a scientific approach you need to compare it to data, otherwise otherwise it's...
No, but I mean, you can compare it to a different set of data. You can use the same model, you can interlink species like bacteria, and then you can control an environment.
It tells you you take the right interactions and adaptation mechanisms in the ecosystem into
No,
account.
but that you don't know until the Antarctic ice extinct, I guess.
For Antarctic, maybe not, but there are some regions, for example in Chile, there is a research station that is located in a, I don't know the word in English, but it's a region where the species cannot be reserved. Reserved is a natural area. And they have 30 years of studies about the presence, absence, and the ecological relationships of the species in this area and in a neighbor area in which it's allowed the fishery or so it's not preserved. So if you see most of the most important works in food web analysis with real data is about this station. So for Antarctic maybe not, but for some regions maybe you can do some.
Okay, and then they are coupled to outside.
They don't have the good model until now, but they have changed in the topology of the food webs reported.
I see lots of hands, so let me see who is and then select a couple of questions. Marina will be next.
So the Arctic food web, that's from the Barents Sea?
Yeah.
Is that likely to be different from, say, the Canadian wilderness tundra?
Yes. Yes, maybe yes. But we performed the studies to the largest food web available because in order to have the best statistical analysis possible. Most of the food webs from Alaska, for example, has only 30 species. So we choose to use just one big food web and not to join, for example, to food webs from so different ecosystems. Like they have all, the central part of Arctic is ice, completely ice. Until now, during the summer, it's only ice. So they have no interaction, no many interactions between these regions. So we choose the region with food web with more species.
And let's select one more. Victor?
So, I mean, considering this as a percolation problem, so I didn't see that the Arctic or the polar food webs are more vulnerable to perturbation because you didn't show me another food web and compare what the percolation properties of this other network with this. Second, and I missed a lot of this thing because this kind of comparative analysis or with a random case, for example, you randomize the network because then you could see what comes from the correlation or what comes just from randomness, and at least you could say something at the comparative level. And second, as all of this is based on small networks and based on observations, so this is very biased.
Yeah.
So what is really the relevance of this thing? So you really can trust, I mean, if the results of this, I mean, if somebody, I mean, if a different team would collect the data, probably the network would be different, right? And the result would be still
for the paper, we have the comparison between these food webs and other marine food webs. And we saw that for Arctic food webs especially, it's very different from most of the food webs of the marine food webs. But I didn't show it here because I would like just to compare Arctic with Antarctic. But I will show you the results we have. And of course, it has a lot of bias, especially because some studies are field studies. Only one research group went to the ocean during 10 or 20 years and studied the trophic relationships. But other studies are based on meta-analysis, so are based in other works. And other studies merge these two kind of strategies, of methodology. So yes, they have bias, And I don't know how to solve it actually, but I assume that it has bias, and in the conclusion of the paper also we just comment like you commented that we need to remember that it has bias. I forgot to put 0.9 here maybe.
I think we should stop at some moment, but there are lots of questions, so let's continue in private discussions. Thank you.